So here is a Chimera graph. It's a very well-known and popular graph, and it's a huge graph here. It's a 10,000 spin problem. So any sampling problem or optimization we want to solve here, we have to deal with 2 to the power 10,000 spin states. To be precise, 10,368 bits. And here is a portion or a tile of the Chimera graph, and as you can see, it's a repeatable tile. And as you zoom out, this is a giant graph. This is a huge 10,000 spin graph, as I mentioned. And such a graph really requires multiple FPGAs, and this is a suitable graph. There are also Pegasus graphs, Zephyr graphs, and if you want to really scale them out, you need multiple FPGAs. So today we are going to demonstrate two different examples. One is sampling or inference, and the other is combinatorial optimization problem on the Chimera instance. In machine learning and AI, sampling is really important because one would need many high quality solutions in a given amount of time if they want to train a large amount of data set. Here we have plotted the ideal mean magnetization curve for the Chimera instance. Here we are basically solving a ferromagnetic instance, meaning that all the spins should be +1 or -1, or their couplings are ferromagnetic. So we are plotting the ideal mean magnetization using a sophisticated algorithm here called parallel tempering at different beta values. And as you can see, this is the mean magnetization, meaning if the spins can be +1, -1, we are taking the mean of the absolute values. And at a very low beta, the mean magnetization is close to 0, meaning that the system is completely disordered. Then after a critical point or a critical temperature, the system comes to order, and at the end, since it's a ferromagnetic, the mean magnetization or the mean of the absolute value become close to 1. So now we'll try to approximate this behavior using CPU and FPGA probabilistic computer and see which one does it faster and with high quality. So let's run with CPU first. So this is the code for the CPU. I'm going to run it on MATLAB. And trust me, this is the fastest I could run the CPU. This is a 10,000 spin graph, and since the keep sampling requires a double for loop, it's very slow in the CPU. So I'm taking only one sweeps per beta. That's why, as you can see, the solution quality is very poor. It couldn't even see the phase transition, or the solution quality, the average is very poor, 17 seconds. At best, what I can do, I can make it 10x for now and see if it improves anything. But ideally, if we want to reach the ideal mean magnetization condition, we would need really many samples, and it would take hours or even days to reach there. So let's see what happens now. I'm making it 10x slower because I took 10x more samples. And let's see. I'll stop the program if I don't see any improvement here. So okay, looks like it's trying to catch it, but let's see if it sees the phase transition. Okay, 4 points complete. It does not look like it's going to see the phase transition because the critical point, I think we already passed it. And one more point, yeah, we passed the critical point. It's still no improvement, and we have already left 50 seconds. So yeah, I think I'm going to quit this one because this is going nowhere. And yeah, in fact, it is dropping. Okay, let's stop this one. And now I will run the same thing on the FPGA. This computer is connected to our FPGA system, and as you can see, like FPGA took 1.03 seconds to approximate the mean magnetization. And here we are using PCI Express connection and doing read memory to read the sweeps from FPGA. This is a MATLAB function that reads from FPGA read memory. So let me run it actually again to see if it's repeatable. Okay. Okay, again 1.03 seconds. Let me run it one more time. This time 0.9 seconds. Another time 0.89 seconds. Okay, it's consistent, and it's always matching with the ideal mean magnetization, which shows that while MATLAB could not approximate it within like even 180 seconds, FPGA can do it within only 0.89 seconds. This shows how powerful this FPGA probabilistic computer is in terms of speed and quality. Now let's move to the combinatorial optimization problem. This time we'll be doing a spin glass problem, which will be very difficult, but the solution is known to us because we planted the problem. So it's called planted icing problem, and we are going to run simulated annealing on both CPU and for the FPGA, and we'll see which one actually reaches the ground energy. So as before, let's start with the MATLAB version or the CPU version. So again, now we are running simulated annealing from beta equals 0 to 10, and this is the fastest I could run. And as you can see, the CPU is trying to reach the ground state, and it took almost 13.37 seconds to reach 91.86% solution quality, which is not really good. Now, let me try another seed to see if it improves anything, because simulated annealing sometimes can get stuck at a local minima. So let's try another run and see if it changes the luck. And as before, it is also having the double for loop, so it's very slow technically. So okay, another run. Let's see what happens. So it reaches 91.90%. And I would change the seed randomly one more time and see anything happens. So okay, 5% gone. So as I said, the ground energy is known, and let's see what happens. So okay, 13 seconds, 91.87%. So it looks like it goes close to 92% at best with this 15 second or 16 seconds of time. Now I'll run the same instance on the FPGA, and let's see what happens this time. Well, FPGA is super fast as before, and within 3.32 seconds, it reached 99.22% solution quality. Okay, I'll run it one more time to see if it's repeatable. This time 3.33 seconds, 99.22% again. Let me run one more time. And FPGA does not need a RNG change because the random numbers inside the FPGAs are running always in the background, 99.14%. So as you can see, in multiple different runs, FPGA can approximate the solution with 99% quality within only 3 seconds, 3.5 seconds at most, 99.31% in this case. While the CPU version suffers, even taking 15 to 16 seconds, it could reach like barely 92%. So these two examples shows how good the FPGA is in taking high quality solutions in a very, very quick time. And this is useful in both combinatorial optimization and machine learning context for sampling. And that's what we wanted to demonstrate today. Thank you very much.